Welcome student, video lecture 6 PCH 2801 unit 3 organometallic chemistry part 6. I am Dr. Devanga Pandya from Department of Chemistry, St. James College, Autonomous, Ahmedabad. Friends, in the previous lecture we have talked about 1,3-butadiene complexes, and here we will going to discuss regarding cyclobutadiene complexes. So what is the changes, and we will going to compare and contrast similarities and differences between 1,3-butadiene as a linear ligand and as a cyclic ligand. How it differs structurally, reaction wise, we're going to discuss that one. Cyclobutadiene complexes. Cyclobutadiene, that is C4H4, is a cyclic planar compound with 4 pi electrons. It is an anti-aromatic compound, and hence it is highly unstable in a free state. So free state will not going to obtain it because the aromaticity does not retain, and as aromaticity would not be there, there is no resonance, there is no resonance stability, and as a result of that it is highly unstable compound. In 1956, L.E. Orgel and S.C. Higgins predicted on the basis of orbital symmetry that cyclobutadiene could be stabilized by coordination to a transition metal element or any metal element. Shortly thereafter, the first cyclobutadiene complex, that is NiCS3C4Cl2 twice, was synthesized by Craig in 1959. Later on, Petit and co-workers prepared an unsubstituted analogous, that is completely cyclopentadiene metal transition metal complex. While taking this brief introduction and our historical background, we can add that after years of attempts to prepare cyclobutadiene in free state, the goal was first achieved by Petit and co-workers in 1965. Cyclobutadiene was isolated in inert matrices at very low temperature, we can say 30 Kelvin. The infrared and photoelectron spectral studies suggest that cyclobutadiene molecule is not a static one. There are two rectangular forms which are in rapid and dynamic equilibrium with each other. That you can see these two in a dynamic equilibrium with each other, rapid dynamic equilibrium with each other, two rectangular forms of cyclobutadiene. In the form 1, carbon 1 and 2 and carbon 3 and 4 bonds are larger than carbon 2 and 3 and carbon 4 and carbon 1 bonds. Conversely, in form 2, C1C2 and C3C4 bonds are shorter comparatively with C2C3 and C4C1 bonds. Cyclobutadiene is a 4-electron donor ligand, and it forms some stable complexes. The cyclobutadiene complex can be prepared by synthetic route, and we have a big synthetic route. The first one is cyclobutadiene complex was prepared by Craig in 1959 using this reaction. We have two substituted cyclic structure, 2 mole substituted cyclic structure treated with nickel tetracarbonyl compound, and here we're going to get the substituted cyclobutadiene complex with nickel and chloride act as a bridge ligand, substituting 6 carbon monoxide ligand from each nickel tetracarbonyl compound. Second route is the cyclobutadiene complex are prepared by the reaction of cis dichlorocyclobutadiene with metal carbonyl. Here you can see that this is a substituted dichloro semi-saturated cyclobutadiene treated with 2 mole of Fe2CO9, and we will going to get the first ever pure unsubstituted cyclobutadiene complex, substituting 6 carbon monoxide, and we're going to get FeCl2 as salt as well. The second reaction, in which the same reagent has been considered with ruthenium, triruthenium deca-2 carbonyl, and it will going to give the same cyclobutadiene pure complex, substituting carbon monoxide over here. And the same third reaction is with molybdenum complex. We're going to get a pure cyclobutadiene molybdenate complex as well, substituting the carbon monoxide. Now in further preparation, the third preparation route is cyclobutadiene complexes can be prepared by coupling reaction of substituted acetylenes. So here you can see tetrachloropalladium will going to treat it with this biphenyl acetyl alkyne compound, 2 mole of it, and 2 chlorine get substituted. We're going to get this substituted cyclopentadiene complex. On further treatment, we're going to get pentadienyl complex converted into butadiene, cyclobutadiene complex. Substitute cyclobutadiene, tetraphenyl group would be there surrounding to it. The same alkyne complex treated with FeCO5, we're going to get the substituted cyclopentadienyl, substituting 2 mole of carbon monoxide. Similarly, another reaction is with molybdenum. We're going to get the cyclopentadienyl complex with molybdenum, substituting for carbon monoxide. And the same way we're going to get this different product as well. The same route and same process is there. From metal acyclopentadiene, we can prepare this complex as well. Here you can see metal acyclopentadienes. This metal acyclopentadiene treated with dimethyl stannous chloride. So lithium chloride gets substituted, and we're going to get this complex. Treated with nickel bromide, we're going to get the substituted cyclopentadiene nickel complex, where bromine acts as a bridging ligand over here, bounding to nickel with cyclopentadiene, butadiene, sorry. X-ray diffraction studies of complex of methyl and phenyl substituted cyclobutadiene suggest that carbon 4 ring is a square planar, and the substituents are slightly displaced out of the plane of C4 ring on the side away from the metal atom. In the structure and bonding, this information can be obtained. The structure of Fe, eta4, C4S6, CO3, we can see in this diagram. Here, these 3 different structure. This is a bridging structure, and this is a pure cyclobutadiene metal complex, where you can see each carbon bond length is of 1.46 angstrom, because they are simultaneously attached with Fe. Eta4 is their hapticity. As a result, all carbon bond length is quite equivalent, that you can observe over here. Similarly, here also you can observe the variation in nickel chloride because of this larger group attached over here. So slightly different bond length between nickel chloride is going to be observed over here. But here, when we talk about cyclobutadiene, again the bond length between carbon is not that much differ. Here you can see 1.46 in a pure, and substituted one we're going to observe a minor change, that is 1.45 angstrom. The free cyclobutadiene molecules is rectangular and anti-aromatic, but the coordinated to a metal, that means coordination can drastically change the property. The cyclobutadiene molecule acquires a square planar shape automatically, and it becomes aromatic. So that is the beauty of chemistry, that a simple coordination can convert a toxic material into a medicinal material likewise. Thus, the unstable cyclobutadiene molecule becomes a stable on complexation. I can give you another example, that on complexation, mercury directly is a very toxic metal element, but on carefully coordination, we can convert the mercury is having a beautiful medicinal effect, even anti-cancer activity as well. So, coordination chemistry can help to convert the compound from different property to the different property as well. Obviously, the cyclobutadiene complexes afford a classical example of stabilization of a ligand by coordination to a metal. In the hypothetical free square planar cyclobutadiene molecule, each carbon atom is sp2 hybridized. Likewise, we have observed in alkyne, allyl, even in 1,3-butadiene, and now in the cyclobutadiene. Every time we found carbon atom in sp2 hybridized, and it forms 3 sigma bonds, 2 with neighboring carbon atom and 1 with hydrogen atom, using its 3 singly occupied sp2 hybrid orbitals that we can see in the valence shell electron configuration of carbon atom over here. And again, it has one unpaired electron which remain perpendicular to the planar arrangement as we observed in the case of alkyl, allyl, 1,3-butadiene, etc. One singly occupied pz or atomic orbital is left unused on each carbon atom perpendicular to the molecular plane, that is xy plane, and that we observe in each case. That is a similarity that we observe in each case, that one pz unoccupied electron having sigma skeleton of cyclobutadiene we can observe over here, and that make this complex more reactive. The 4 singly occupied parallel pz atomic orbital take part in the linear combination forming 4 pi molecular orbitals. We can see in this diagram, this is the increasing energy, and these are the 4 unoccupied single electron containing 2 pz orbital on each carbon perpendicular to the planar arrangement of the cyclobutadiene sigma skeleton, and that is going to form our 4 pi molecular orbitals, psi1, psi2, psi3 and psi4. Probably like this 2 kind of arrangement would be there, and that make availability of this 2 pi electron make this compound more reactive, and more reactive the resulting complex would be as well. Now the square planar cyclobutadiene has 2 unpaired electrons in molecular orbitals psi2 and psi3. It is unstable electronic configuration because it is the characteristic of anti-aromatic biradical, and in actual way we are going to practice cyclobutadiene is rectangular with no unpaired electrons in it. On coordination to a metal provides further interactions to avoid this unstable electronic configuration. The pi molecular orbital of cyclobutadiene and the atomic orbitals of metal atom with matching symmetry are given in this figure, that is psi1, psi2, psi3, psi4, and with this we can get the matching symmetry of the metal orbitals. You can see pz, that is for sigma bonding, dz square, that is for sigma bonding, and s orbital would be there for sigma bonding as well, and dyz zx, that is for pi bonding, and dx square minus y square, that is for theta bonding as far as metal atomic orbital is concerned. And with the same symmetry of cyclobutadiene, when it match, we're going to get the bond formation between metal and cyclopentadiene. The vacant s orbital, pz orbital and dz square atomic orbital of metal atom overlap with the filled psi1 molecular orbital of cyclobutadiene, forming ligand to metal sigma bond. Similarly, the field dx square minus y square atomic orbital of metal atom overlap with the vacant psi4 molecular orbital of cyclobutadiene, forming metal to ligand delta bond, or we can say theta bond. But the main binding force which provides stability to cyclobutadiene complexes originate from the overlapping of singly occupied psi2 and psi3 pi molecular orbital of cyclobutadiene molecule with singly occupied dz and dxz and dyz atomic orbital of metal atoms. And that is in this way we can observe that formation. You can see psi2, psi3, and this is the xz and yz, and that overlap will going to result into pi1 and pi2. That is how pi molecular orbital in butadiene complex is going to be observed, and the bond order would be 2. So this indicates the partial molecular orbital of cyclopentadiene complex. As a result of pi molecular orbital like pi1, pi2, pi1 star and pi2 star are formed, that is 4 pi molecular orbital is formed. The bonding pi molecular orbital, that is psi1 psi2 over here, sorry, pi 1 pi 2 over here, filled with high degree of ligand character. And thus the coordinated cyclobutadiene gain partial control of two more pi electron coming from meta atom, and its electronic configuration would be psi1 2 pi 1 2 pi 2 2, resembles that of the aromatic 6 pi electron dianion, that is R4C4-2, and hence it shows aromatic character. This coordinated cyclobutadiene now converted into aromatic nature, as already I've said. Here, the first ever synthesized cyclobutadiene complex is a red violet in powder form. This is the property we are discussing. It is soluble in water and dichloromethane. This pure cyclobutadiene complex is a remarkably stable compound, and electrophilic substitution reaction, when we discuss in the property, like C5H5, that means cyclopentadiene ring in for ferrocene, this cyclopentadiene MnCO3, the C4H4 ring of cyclobutadiene complex is aromatic, and it undergo typical aromatic electrophilic substitution reaction, and that we can observe over here the substitution reaction simultaneously with acid chloride, aldehyde, H2SO4, anhydride, and mercuric anhydride as well. In presence of NaCl, we're going to get different substituted product of cyclobutadiene with methyl complex, and they have their own different properties and application. Second property is the oxidative decomposition. When cyclopentadiene ion carbonyl 3 tetracarbonyl ion complex is treated with cerium salt, cyclobutadiene is liberated as a result of oxidative decomposition reaction. Cyclobutadiene liberated in this way may undergo various organic reaction in situ, as we can see in this next slide. Here the in situ reaction is there. Fe cyclopentadiene complex treated with cerium salt will going to give cyclobutadiene substituted from iron, and much in the same way these two reaction will going to give in situ reactions over here. Third is a nucleophilic attack. The cationic cyclobutadiene complex may undergo nucleophilic attack also. So here the reduction of this complex will going to give this substituted product. Reduction of this complex will going to give triphenyl carbide complex, hydride complex over here. So on substituting with trialkyl phosphine, it will going to give us this substituted product. Well, thank you very much for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.